Testing, can you hear me? Hello? Alright, I'm public now. So I'm going to be learning calculus again. I will just continue from where I left off last time. I read about triple integrals. I did not do a lot of exercises, but I did read through it. And I'll just read the next chapter as well. Okay. We have already discussed a few applications of multiple integrals, such as finding areas, volumes, and the average value of a function over a bounded region. In this section, we develop computational techniques for finding the center of mass and momentum of inertia of several types of physical objects. Sorry, I have a sore throat, so I'll be coughing a lot. The center of mass, also known as the center of gravity, if the object is in uniform gravitational field. If the object has uniform density, the center of mass is the geometric center of the object, which is called the centroid. Figure 5.64 shows a point P as a center of mass of a lamina. The lamina is perfectly balanced about its center of mass. To find the coordinates of the center of mass of a lamina, we need to find the momentum of a lamina about the x-axis and the moment about the y-axis. Okay, so the vertical direction is the z, and then the two horizontal ones are the x and y. Wait, should I read this chapter as well? I'll just revise this chapter and then I will go back. Okay, so center of mass and moment. Let's begin by looking at the center of mass of a one-dimensional context. Consider a long thin wire or rod of negligible mass. It is resting on a fulcrum, as shown in figure 2.62. Now suppose we place objects having mass m1 and m2 at distances d1 and d2 from the fulcrum, respectively as shown in figure 2.62. The most common real-life example of a system like this is a playground seesaw. On a seesaw, one child sits at each end, the heavier child sinks down, and the lighter child is lifted into the air. If the heavier child slides in towards the center, though the seesaw balances. Applying this concept to the masses on the rod, we know that the masses balance each other if and only if m1 d1 is equal to m2 d2. In the seesaw example, we balance the system by moving the masses with respect to the fulcrum. However, we are interested in systems in which masses are not allowed to move. Instead, we balance the system by moving the fulcrum. Suppose we have 2 point masses m1 and m2 located on a number line at points x1 and x2. Respectively, the center of mass is the point where the fulcrum should be placed to make the system balanced. Okay, so this point is the balancing point. Thus, we have m1, the balancing point, minus x1. So this distance should be equal to m2, and then x2 minus the balancing point. m2 times this distance should be equal to m1 times this distance. And then the formula for the x is m1 x1 plus m2 x2, then divided by the total mass. The expression in the numerator is called the first moment of the system with respect to the origin. If the context is clear, we often drop the word first and just refer to this expression as the moment of the system. The expression in the denominator is the total mass. Thus, the center of mass of the system is the point at which total mass could be concentrated without changing the moment. The idea is not limited just to point masses. In general, if n masses m1, m2, and mn are placed on a numbered line at points x1 to xn, respectively, and the center of mass of the system is given by, we have this, and then the total mass. And this capital M, it's called the moment of the system, right? You can generalize this concept to find the center of mass of a system of point masses in a plane. Let M1 be a point mass located at point x1, y1 in the plane, and then the point mx of the mass with respect to the x-axis given by mx is equal to m1, y1. Similarly, the moment my with respect to the y-axis given by my is equal to m1, x1. So m1 times x1 is the moment with respect to the y-axis. And notice that the x-coordinate of the point is used to calculate the moment with respect to the y-axis and vice versa. The reason is that the x-coordinate gives us the distance from the point mass to the y-axis. Oh, if there was like a seesaw here, they're balancing on the y-axis. So that's why we are checking the x, how far are we from the y-axis. So mx is all the m mass times y, and by the moment in the y-axis would be the mass times the distance from the y-axis. Also, the coordinates of the center of mass of the system are, so with x is my divided by m, with y it's mx divided by the total mass. Suppose 3 point masses are placed in the xy plane as follows. Find the center of mass. So let's see. -1, 3. We have this point. We have 1, 1, 1, 1, 2, -2, 2, -2. So if these points, hold on. We need to find the moment with the x direction. Like if these points were on a seesaw on the x-axis, Okay, so we need to find the balancing point with x. I should just write it here. So we have -1, +3. We have 1, 1. We have 2, -2. Okay, so if you want to find, let's say intuitively x naught is somewhere over here. How do we find this? How do we find the balancing point just in the x direction? So we take the distance from the balancing point, which is their y value. So 2 xy. So yeah, yeah. This, and then plus it with 6. This, plus it with 4. This, and then 6 for 2, 12. And then 2 times 3 plus 6 minus 8. Divide all of that by 12. 0.33333. Is that correct? It's like we are finding the average mass, but we are giving more weight to one mass than the other. And masses can also have negative weight. Okay, 0.333. That's the balancing x point. Now for the balancing y point. -1, 1, and 2. -1, 1, and 2. 2, and then 6. 4 times 2 is 8. 14. Okay, then we left with 1. So this is the balancing point in the y-axis. So in both the x and y-axis, we have 1 and 1/3. So far we have looked at systems of point masses on a line and in a plane. Now, instead of having a mass on a system concentrated at discrete points, we want to look at systems in which mass of a system is distributed continuously across a thin sheet of material. For our purposes, we would assume the sheet is thin enough that it can be treated as if it is two-dimensional. Such a sheet is called a lamina. Lamina are often represented by a two-dimensional region in a plane. The geometric center of such a region is called its centroid. Since we have assumed the density of the lamina is constant, the center of mass of the lamina depends only on the shape of the corresponding region in the plane. It does not depend on the density. In this case, the center of mass of the lamina corresponds to the centroid of the delineated region in the plane. Based on these, we first consider lamina in the shape of a rectangle. We call that the center of mass of a lamina is the point where the lamina balances. For a rectangle, that is both the horizontal and vertical center of the rectangle. Based on this understanding, it is clear that the center of mass of a rectangular lamina is the points where the diagonals intersect, which is a result of symmetry principle. The symmetry principle: if a region R is symmetric about a line L, then the centroid of R lies on L. I mean, it's true if the masses are evenly distributed. If it weighs more on one side, then it would be different. Let's turn to a more general general laminas. Suppose we have a lamina bounded above by a graph of a continuous function f of x. Suppose by the x-axis we are on the left and right by the lines x is equal to a and x is equal to b respectively as shown in the following figure. As with systems of point masses, to find the center of mass of a lamina, we need to find the total mass of a lamina as well as the moments of a lamina with respect to the x and y axis. As we have done many times before, we approximate these quantities by partitioning intervals a, b and constructing rectangles. So the distance from x, right? To approximate the mass of the lamina, we add masses of all rectangles to get this. So what is this? In this case, rho is expressed in terms of... So this rho represents the density of the lamina. In this case, rho is expressed in terms of mass per unit area. So I have rho times height, rho times the area of that particular region. That gives you the mass of that particular area. And then we are summing all of those rectangles to get the total mass. Next, we calculate the moment of the lamina with respect to the x-axis, returning to the representative rectangle. Recall that its center of mass is xi. Okay, just for this rectangle, for a rectangle, it's close xi divided by 2, then fxi divided by 2. Hold on. Yeah, the point is at xi. So we take that xi point, then f of xi divided by 2. X, sorry, this x star is the middle point, right? Yeah, x star is the midpoint. So x star is the midpoint and the center of mass is f of xi divided by 2. This will be very small, so it's going to be really close to a rectangle. Recall also that treating the rectangle as if it is a point mass located at the center of a mass does not change the moment. Thus, the moment of the rectangle with respect to the x-axis given by the mass of the rectangle multiplied by the distance from the center of mass to the x-axis. Therefore, the moment with respect to the x-axis of the rectangle is rho. Okay, rho all this. So the moment of the rectangle with respect to the x-axis is given by the mass of the rectangle. So the mass is rho f of x star delta theta. Okay, the mass is density times area. Density times the area, and then area is this times the interval, the y value times the interval, and the moment of just this rectangle is rho this multiplied by this center of mass. Sorry, the distance. The moment with respect to is this. So the moment is this, right? So the moment is this numerator, which is mass times the distance. Mass times the distance. but this is not a point mass, this is a rectangle. So the distance we are considering is the center of mass of that rectangle. So mass times the distance. Distance is like distance from center of mass. So f of x star divided by 2. That is for just this rectangle. Adding the moments of the rectangle and taking the limit of the resulting Riemann sum, we see that the moment of the lamina with respect to the x-axis is, we take the limit and we take the rho out, the density out, and then we are left with this. We can take 2 out as well, right? The moment with y is, so rho times f of x star times delta x, that's the mass, and the distance of the rectangle is just the xi value, right? So we have rho, the integral of x, f of x. Right. Let's do this. Copy, paste. Let R be a region bounded by the graph of the function f of x is equal to, okay, let's see. I'm assuming it's something like this, right? Root x. Want to see a graph. Square root x. Actually, y is equal to. Sorry, this is, I drew a log graph. Root x. Let R be a region bounded above by the graph of the function root x and below by the, okay, 0. So we are considering all this. Find the centroid. So if we divide it into rectangles and the in we find the distance with respect to the x-axis, we get something like mass for the x is something like rho integral 0 to 4 square, right? F of x dx, that's the f of x dx, and rho, that's the area of the rectangle. But since it's a rectangle, the midpoint is f of x divided by 2. Well, at least the midpoint in the from the x-axis, the distance from the x-axis. Then we have x over 2, the root cancel out. X square 0, 4. What's the row? Find the centroid of the region. What is the, do we assume that the mass is just 1? Density is 1? 4 minus 0, so 8. We got this. And then for y, it's like this is, we have the area. This is the area. And then the distance from the y is like just the x value. 5/2 divided by 5/2 by double by 2/5. Yeah. 0 doesn't matter. 5/4 5/2. But then what did the centroid of the region? Do we assume the density is 1? It's root x. Hold on. How did they get this as 4? Uh, let's assume rho is equal to 1. Alright. But then the root cancels out. That is true. Oh, when you divide it. Okay, okay. I multiplied it by 2. So there should be 4. What about the y? 16/3. Or to the power of 5/3. 5/2. It's 2.5. 2 times. And then we divide it by 5. Got 12.8. 64/5. Yeah, it is 64/5. And then we find the center, right? Total mass which is 4 density plus 64/5 density divided by the total mass. M is equal to from 0 to 4 density times the area under the graph. So half becomes 3/2 divided by 2/3 or 0. 2/3. 5 over and then yeah, this is the 16/3 mass. So this is equal to, this row will cancel out. 16. You can multiply this by 3. 16.8 what is 16? 3.15. 3.15 and 3. Wait. No. Hold on. No, what am I doing? We just need to do x and y separately, right? So we have 4 row. Any times 4 is 12 over 16. Divided by 4, we get 3 over 4. Y 64 over 5 divided by 16 over 3. 64, 5, 16. 16, 2.4, 2.4. Yeah, 2.4. We stated the symmetry principle earlier when we were looking at a centroid of rectangles. The symmetry principle can be a great help in finding centroids of regions that are symmetric. Consider the following example. Four minus x square. Oh, so it's somewhere here on this line. But the mass is not the same, right? We just need to find the y. Yeah, the y one. This section ends with a discussion of the theorem of Pappus for volume, which allows us to find the volume of particular signs of solid by using the centroid. Let R be a region in the plane and let L be a line in the plane that does not intersect R. Then the volume of the solid of revolution formed by revolving R around L is equal to the area of R multiplied by the distance d traveled by the centroid of R. Okay, let's just go to the previous chapter. So if we allow a constant density function, then x is m by over m, and y is mx over m. Then these two give the centroid of the lamina. Suppose the lamina occupies a region R in the xy plane, and let the rho, is this p or this rho? Rho xy be its density in units of mass per unit area at any point xy. Hence, rho xy is equal to limit, so mass divided by area, and the limit as area goes to 0, where delta m and delta a are mass and area of a small rectangle containing the point xy. And the limit is taken as the dimensions of the rectangle go to 0. Just as before, we divide the region R into tiny rectangles Rij, the area A, and choose x star, y star as sample points. Then the mass Mi of each Rij is equal to the rho x star, y star, delta A. Let KNL be the number of subintervals in xy respectively. Also note that the shape might not allow or always be rectangle, but the limit works anyways, as seen in the previous sections. Hence, the mass of the lamina is we have this rho x star y star delta A, and then rho xy dA. Then we integrate over the entire region. Consider a triangle and lamina R with vertices this and a density xy. Find the I will just skip that. Now that we have established the expression for mass, we have the tools we need for calculating moments and center of mass. The moment mx about the x-axis for R is the limit of the sums of moment of the regions Rij about the x-axis. Hence, mx is y, the distance from the x-axis, times the density for every point dA. My is x times the density dA. Consider the same rectangular laminar with these vertices with density this. Find the moments mx and my. Let's do this. So 5.56. Y rho x y dA. So from what region to what region? 0, 0, 0, 3, 3, 0. Hold on. 0, 0, 0, 0, x, y, x, y. 0 to 0 to 0, 3. 0, 3 to 3, 0. So hold on. This is equal to x, y. And then y from these 2 points is equal to 3 minus x, right? But I think it's easier if I do this. I just multiply the y squared dA. So y would go from 0 to 3 minus x. And then x would go from 0 to 3. Then we have first we derivative with respect to y, then x. So first we have x cubed over 3 minus x 0. T cubed. Actually, let's just see the answer. Wait, they just skipped the entire thing. Okay, let's just go through it. I want to use the binomial theorem, but never mind. 3 minus x, 3 minus x, and then 3 minus x dx. 339 is 6 plus x. 27 9x 18x and then 6x squared plus 3x squared minus x cubed dx. Imagine if I'm wrong. 9. Yeah, 9x here. Okay. This becomes 3. 3. This also becomes 3. No, yeah. This becomes 4. This becomes 4. This becomes 5. I don't wanna do all this. Well, I'll just use a calculator then. Over 2, 3 square plus it with minus 3 cube. I'll just write x minus 6x cubed minus 6x cubed plus 6 over 4 plus 6 over 4 x cubed plus 3 over 4 plus 3 over 4 x cubed. Now x to the power of 4 minus 3 and minus 22 minus x to the power of 5 over 5. Something is wrong here. 81 by 20 divided by 2. Or actually, instead of writing that, I should write I should write yeah, I'm wasting too much time on this. I have to 3 times 3 9. This seems correct. 27 minus 9 minus 18 plus 6x squared. Yeah, this seems correct. Then I just added x at the end, right? 4, then 2, this became 3, this became 3, this became 4, this became 4, and then this became 5. Okay, I don't know what the issue is. I'll have to look at it later. What is the correct answer anyway? 80 or 81 divided by 22. Yeah, I will look at it later. Then we have my divided by mx divided by m. Use the previous formula divided by the mass. Centroid is the center of mass, right? Not necessarily the geometric center. For a clear understanding of how to calculate moments of inertia using double integrals, we need to go back to the general definition of moments and center of mass in section 6.6 of volume 1. The moment of inertia of a particle of mass m is about an axis is mr square. It has r is the distance of the particle from the axis. As we can see from figure 5.66, the moment of inertia of the subrectangle Rij about the x-axis is I star square and the rho xy delta A. Figure 5.66. So moment of inertia of a particle of mass m about an axis. So we are using the distance. So it's like as if it's rotating from the origin, right? It's revolving around the origin. The moment of inertia I about the x-axis for a region R is the limit of the sum of moments of inertia of the regions Rij about the x-axis. Hence, we have this, and then we have this. So they're using y squared instead of y previously. Oh, the total inertia is just added. Ix plus Iy. As mentioned earlier, the moment of inertia of a particle of mass m about an axis mr squared, where r is the distance of the particle from the axis, also known as the radius of gyration. Hence, the radii of gyration with respect to the x-axis, the y-axis, and the origin are this, and then Iy over m, square root all of that. The radii origin I naught over m, square root all of that. Okay, this time in 3 dimensions, we have a density function defined like this. Sorry, the mass is defined like this. The moment in the xy plane is the distance from z, and from the xz plane is the distance from y, and lastly we have the distance from x. Okay. All right. I skipped through the inertia part, but I'll have to go somewhere soon, so I will end the stream here. And yeah, I'll see you guys next stream then. Anyways, bye then.